So let's talk about a clear set of examples where red light and near-infrared light have been shown to have positive effects on our health. And these are the data that I referred to at the beginning of the episode from Dr. Glen Jeffery at University College London, who, again, is a long-standing member of the neuroscience community working on visual neuroscience, and who over the last decade or so has really emphasized the exploration of red light and near-infrared light for restoration of neuronal function as we age. This is absolutely critical. We know that we don't accumulate many new brain cells as we get older, and in some areas of our nervous system, such as our neural retina, which is the part of our eye that's responsible for translating light information to electrical signals so that we can see, we don't get any new cells after the time in which we were born. So the ability to keep our neurons healthy is extremely important for our visual system, extremely important for our hippocampus, an area of the brain involved in memory. And I should just mention that even if people don't get Alzheimer's, there's always going to be some degree of age-related dementia. Sadly, nobody is as cognitively sharp in the years before they die as they are 20 years before that. It's just never the case. We're all getting worse at thinking, feeling, perceiving, etc. The question is how quickly we are getting worse. So any mechanism by which we can preserve or reverse neuronal function turns out to be immensely beneficial. The Jeffrey Lab has published 2 studies in recent years on humans that looked directly, no pun intended, at how red light and near-infrared light can improve visual function. I'm going to describe the parameters of those studies, and then I'm going to describe what they found exactly. The mechanistic motivation for these studies, again, traces back to this effect of light on mitochondria. So to go a little bit deeper into that mechanism just briefly, so that you can frame any potential protocol that you would develop. When light arrives on cells, including neurons, that light can penetrate into the cells if it's of the appropriate wavelength. Red light can do that. It can get into cells. It can access the mitochondria. It can increase ATP. In general, anytime ATP is doing its thing to increase energy in cells, it's involving this thing called cytochrome C, which is an oxidase. Anytime you hear ACE, A-S-E in biology, it's going to be an enzyme. It's involved in some process of degrading a molecule and creating another molecule typically. So ATP and cytochrome C is going to give you ATP. Now that's a great thing, but it creates a byproduct. It breaks things down such that you get these ROSs, these reactive oxygen species. And those reactive oxygen species, for those of you that want to know, are involved in things like redox signaling, and reactive oxygen species actually change which genes are made in a cell. So the goal of any treatment to keep neurons or other cells youthful and functioning well, and to prevent or reverse aging, is going to be to increase ATP and to reduce reactive oxygen species. And in doing so, to disrupt some of the normal pathways associated with aging. The Jeffrey Lab approached these studies with that understanding of how mitochondria and reactive oxygen species and ATP work. And what they did was exquisitely simple to the point of being elegant. And what they found was really, really exciting. What they did is they had people, subjects that were either younger, so in their 20s, or 40 years old or older, view red light of about 670 nanometers. 670 nanometers would appear red to you and me. They had them do that, at a distance that was safe for their eyes, so at about a foot away. Now, a foot away from a very intense red light could actually be damaging to the eye, so they had them do this at about a foot away from a red light that was of low enough intensity that it did not damage the eyes. And they had them do that anywhere from 2 to 3 minutes per day. And in one study, they had them do that for a long period of time of about 12 weeks. And in the other study, they had them do that just for a couple of weeks. What's remarkable is that when you collapse the results across these 2 studies, what they found is that when looking at these subjects ranging from 28 years old to about 72 years old, the major findings were that in individuals 40 years old or older, so in the 40 to 72-year-old bracket, but not in the subjects younger than 40 years old, they saw an improvement in visual function. That improvement in visual function was an improvement in visual acuity, meaning the ability to resolve fine detail, and using a particular measure of visual function, which is called the Triton exam, Tritan, Triton exam, which specifically addresses the function of the so-called short wavelength cones, the ones that respond to green and blue light. They saw a 22% improvement in visual acuity, which in the landscape of visual testing is an extremely exciting result. Okay, so I think in most studies of improvements of vision, you'd be very excited to see an improvement of 5% or 10%. So a 22% improvement in visual acuity, even though it's in this very specific form of visual testing, this Triton exam,